Oh, you are sharing.
Okay. Welcome back, everybody. It was a short coffee break, but now we have an exciting session ahead, so I hope you're caffeinated. We're going to start the first paper session with He-Sun. The session is about volumetric imaging, and we're going to hear about topics from astronomy to biomedical imaging, so a very exciting session. He-Sun, you can take it away.
Okay, thanks. Hello, everyone. Thanks for being here. I'm He-Sun. Work on reconstructing satellites in 3D from amateur telescope images. This project was led by my graduate students, Zhiming, Chang, and my friend Boyang Liu, who is a famous astrophotographer in China. Unfortunately, both of them cannot make the meeting, join us today due to visa, so I will present on behalf of him, but all credit should go to them. Over the past 60 years, the population of artificial satellites has exploded. In particular, in the past 10 years, annual launches into the low Earth orbit have climbed from a few hundreds to nearly 3,000 every year, especially with the mega constellations like Starlink now online. The space environment become very, very crowded right now. So space situational awareness has become more critical than ever to ensure the safe, orderly, efficient use of our orbital environments. However, conventional monitoring relying on professional telescopes or even more expensive spaceborne sensors, which suffer from limited global coverage and high operational cost. At the same time, we've seen the amateur telescope market expand rapidly. This chart shows the annual revenue trend of the amateur telescope market, which has risen steadily in recent years, exceeding more than 200 million every year. This growth indicates that these instruments are becoming more affordable and widespread. So this motivates us to ask, can we leverage the data collected by those accessible devices to do something truly valuable? Before that, let's take a look at how these amateur telescopes really differ from our professional observatory. On the left, you can see a professional telescope. It features much larger aperture, which produce sharper images with richer details. But at the same time, the system are massive. They occupy tens of square meters, fixed in place, and operated by specialized staff. But in contrast, the amateur telescope is low cost, easy to operate, and portable enough for balcony or rooftop deployment. So these devices are far prevalent worldwide, making them real world applicable and maybe have better outreach potential. That brings us to our central question. Can we reconstruct the 3D model of satellites given a short, noisy video of a fast-moving satellites, which are blurred by atmosphere turbulence, degraded by the light pollution, and recorded over only a limited angular sweep? This task turns out to be very challenging. These are samples of the Chinese space station on the left-hand side and the International Space Station using our own amateur telescope. As you can see, the raw frames exhibit severe blur, distortion, and low signal-to-noise ratio, far more extreme than natural images we used in classical 3D computer vision tasks. Moreover, because our camera must remain fixed on Earth, each pass provides only a brief narrow view glimpse. This factor poses formidable obstacles to both post-estimation and 3D reconstruction. traditional geometric method or other nerve-based approaches simply cannot cope with such degradation. Here we designed a complete automated pipeline to address these challenges. Our method solved the problems in 2 stages. First, we developed a hybrid image processing module that combines the classical signal processing and modern deep learning method to enhance the input image quality. And second, we proposed a novel Gaussian splitting-based algorithm that jointly optimized the pose and geometry. I will now walk you through our workflow in detail. Our pipeline first starts with an image processing pipeline that fuses classical techniques with state-of-art video restoration foundation models. I won't spend too much time on this part due to time limit, but you can, as you can see, we combine the classical centering, cropping, Lucky imaging, and the wavelet-based sharpening with the VRT, video restoration transformer, which is trained on a large scale of the natural images. We find the combination of the traditional method and the deep learning method will significantly enhance our reconstruction quality. Here you can compare the raw frames with our pre-processed output after each step. You can see how the atmospheric blur and the speckle noise are efficiently removed, revealing fine details like the solar panel stress textures. And this high-quality pre-processed frames lays a solid foundation for our core objective, the joint estimation of the poses and the 3D geometry. Similar to conventional 3D reconstruction, our 3D recovery begins by extracting and matching the features to initialize the camera poses. We leverage the state-of-art foundation model superpoint and superglue rather than conventional color maps default SIPs implementation for this task because they can provide denser detection, more accurate feature matches, and demonstrate greater robotics on our blurred, noisy frames. And since the satellite's geometry is usually highly symmetric, we also modify the standard structure from motion method by registering frames sequentially one by one. Because this will only match the adjacent frames, so we can avoid symmetry-induced pose errors. Because sometimes when the satellite flips, we cannot distinguish whether we see that from the front or from the back. And we also assume the orthographic projection. So because our satellite is very far from our telescope, so the sensors were placed approximately collinear. Finally, the most important part with the rough pose estimates and the coarse point cloud at hand. Now we can do the joint pose estimation and the Gaussian splitting based reconstruction. One of our key observations is that the reason that the traditional 3D reconstruction method always fails with the low quality image, mainly because they overfit to the noises and the high frequency artifacts too quick before our model learns correct geometry. This challenge becomes more significant if we consider the coupling of the geometric errors and the pose estimation errors. So our solution to this challenge is that we control the growth rate of the point cloud during the training. As illustrated in this animation, our algorithm alternates between optimizing the Gaussian points, cloud, and refining the camera pose. However, at the beginning stages, where the camera pose is not that accurate, we force our algorithm to use very few, or around only tens of Gaussian primitives to feed the image photometrically. This forces our model to learn the rough geometry first. So think about that. We just build the satellites with only 20 very large Gaussian. And this will help our model to learn the geometry first. After we learn the rough geometry, we do the Gaussians, we split the Gaussians and try to increase the number of Gaussian primitives to gradually add more details. But that cannot solve everything, right? Because after we training for a long enough time, it will still overfeed to the high frequency artifact. And so in addition to control the Gaussian growth rate, we also take advantage of the properties of the Gaussian splitting and actively added the Gaussian points to get rid of the outliers introduced by the noise, background, and the atmospheric disturbance during the training. As an explicit volumetric representation method, the 3D Gaussian point can be easily and efficiently edited with a series of outlier rule-based outlier filter, as shown in the training schedule below, by repeating between the control, the growth, the explicit point filtering, and the brush and band pose estimation, we can finally reconstruct a very high quality 3D model. Finally, we've shared one hardware tricks we used during our image acquisition. In the atmospheric tracking, we typically use actuatory mounts to follow the motion of the celestial target due to the Earth's rotation. This mounts operate based on two main rotation axes: the right accession aligned with Earth's rotation axis and the declination axis perpendicular to the RA. However, this doesn't work well for our fast-moving satellites because there will always be meridian flips during our observation. And if we didn't get rid of that, the meridian flips will introduce around half minutes tracking stop. So we cannot capture a very good video. Our solution is very simple. We just swap both axes. So we can keep tracking our satellites during the around several minutes of the satellite's motion, so we can capture very high quality videos for our 3D reconstruction. Let's finally check the 3D reconstruction result of our method. This slide shows the reconstruction result of our method on both simulated data and real on-sky observations, the China Space Station and the International Space Station. As you can see, in the challenging International Space Station cases, despite the severely blurred input, our recovered 3D point cloud still produces consistent and meaningful structures. The non-view system result is not that good because of the very sparse view, but the 3D point cloud is still very high quality. And we also conduct some quantitative comparison, and definitely we achieve the best score. And we also conduct ablation studies to evaluate the contribution of each module, none of them can be missing in our pipeline. And to validate the accuracy of our method, we also performed the metrology on the reconstructing model of the Chinese space station. And as shown in the table on the right, our metrology result aligned closely with the official ground truth with errors generally within 1 meter. Okay, in conclusion, we propose a 3D novel imaging framework for reconstructing satellites from ground-based telescope images. Usually the amateur telescope images with very low quality, and definitely it's not perfect. Sometimes we find we were bothered by the reflections of the satellites, and we are still working on the surface modeling to accomplish those tasks. And you can scan the QR code to see more results about our work. Thanks.
Thanks a lot. We have a couple of minutes, maybe one or two questions.
Thanks, sir, for the talk. My question is about if you amateur telescopes spread across geographical regions, how much would that improve these reconstructions?
Oh, that's a really good idea. Yeah, I think that's definitely improve a lot because now, since we only have one telescope, our coverage of the angles of the observations is very limited, and that's the major reason that we cannot get a really good novel view synthesis. And if we have multiple telescopes, definitely we can improve our reconstruction quality. The only problem is that we have to, for multiple telescopes, we have to place them in different size, and we don't have so many people to do that, but we will try that. Yeah. Thanks.
Maybe we'll take another question while the next speaker can set up. Okay, so if there are no questions from the audience, maybe I'll ask you kind of a broad question.
Yeah.
Where do you see this? So it seems like a citizen science project. Where do you see it taking off in the future as a kind of like on a global scale?
I haven't thought about that, but yeah, but we really want to encourage people across the world to try to see that. But now we only do some, like a very simple cases where the cell size is pretty large. But I think our ultimate goal is that to encourage people across the world to help us to do the space situational awareness to help keep our space environment safe. And I think that's have very broader applications. Yeah.
And that's awesome. Okay,
thanks
a lot, Her. The next speaker, Charlie Bouman, is going to talk to us about view selection in tomography.
Yes. Thank you very much. Let's see if this works. Oh, it's giving me an option here. What am I supposed to do? Okay, I have no idea. Entire screen? Should I set this? Which of these three options should I take, do you know?
Try entire screen.
Should I do this one here? Okay. Let's see if it works.
Yeah, it worked.
Okay. All right, good. Okay. Thanks. So I'm presenting this paper today, but the person who really did the work is Jingsong. Bad about that, and I'm putting his picture up there so you can see him. But I'm also did the work collaboratively, obviously, with Oak Ridge National Laboratories and Venkatakrishnan and Amir, Ziabari, and Greg Buzzard and Obaid. Okay, and I'm Charlie Bouman. Okay, so now in additive manufacturing, you make each part from a CAD model, and in applications like that are mission critical, like if you're making, in this case, these are parts for a nuclear reactor or aviation parts. A classic example would be manufacturing fan blades for a jet engine. You have to have 100% inspection, so every part has to get inspected to make sure it's correct. So you have and typically this might be done with CT scanning. So you have a cone beam CT scan, and then you check the part for to make sure it's correct and it doesn't have defects. And a CT system is really very simple. You just take a source of X-rays, you take a flat panel detector, you put a part on a rotating table, and you attach everything together with a computer and spin it around, and then you image it, and then you reconstruct, okay? And the problem is that, one thing that's really interesting is that the size of this data is just growing unbelievably. Like, okay, so the standard scanner might have a 2K by 2K sensor on it, but our collaborators are telling us they're going to get 10K by 10K sensors. So that's every time you double the size of the one dimension, that's 4 times the data for view, but it's 8 times the data. Okay, so every time it's just growing out of control, okay? So it's an enormous problem. But anyway, and each view can take a long time to take because you have to scan the X-rays through the metal, so it can be very slow, very slow to scan each part. Okay, so the solution, or at least a partial solution, is to use sparse view CT. So not take a complete set of views. So instead of having to take 1,000 views, maybe take 400 or something like that, or a couple hundred, okay? And so traditionally people use filtered back projection or FDK to do reconstruction for tomography. And the truth of the matter is that, and I hate to admit this, but I must admit it, that's how most CT is done, okay? With filtered back projection, but it doesn't work for a sparse view. So if you're going to do filtered back projection, you got to take a full set of views, okay? So one reason people haven't gone to sparse view is because of filtered back projection. But we're trying very hard to make practical software so people can really do iterative reconstruction, what we call model-based iterative reconstruction. Everybody in the room knows about this sort of thing. It's just regularized inversion. But even though we've been publishing about it for 10 years, more years than I'd like to admit, nobody actually does it in real life because it's too hard. So we're trying to make software that makes it practical. And okay, I have this, and I just want to point out that the things I'm going to talk about today are implemented in our software, okay? They actually are implemented. So, okay, so now people are starting to get interested that I can do sparse view CT for parts. Okay, now if I'm going to do sparse view, well, should I take uniform views or should I select the best views? So then what are the best views to take? Okay, well, if you don't know anything about the part you're scanning, then it would be uniform. But if you know something about the part, then take the views that are best for that part. Okay, so, okay, what does that mean? Well, intuitively, there's two things you want to do. One is that you want the views to be informative. So people have learned empirically in the industry, if you talk to them, that they know take the views along the edges, okay? That makes perfect sense, right? So if you have edges, align the views with the edges. I mean, it might not be true, but it is true practically when you do it, okay? However, that's not completely simple because this is cone beam, or so it's a band, so that a single view is not at a single angle, so you have to figure it out for the situation, but you can figure something out. But the problem is, and it's not just that, they also have to be diverse. So if you take all the views so they're all aligned along the major edges, well then you won't get enough diverse information. So you also want the views to be diverse. You don't want all of them clustered together, you want them separated apart. So as a practical matter, so the people have started to study this. There's been some research in this area. I wouldn't say it's been very extensive, but most of the methods come down to something like a balance between being informative and being diverse. So you have some kind of two cost function terms that you heuristically design, and then you have a crazy parameter that you don't know how to pick that blends the two, and you try to adjust it to get a good result. Okay, and okay, so the point here is that you have to know something about the object you're scanning so that you can pick the best views. So there's a little bit of a chicken and egg issue, but I will defer that. So I'm going to give you the answer to the question first, and then I will talk about where it came from, okay? Because I thought maybe that would be an easier way to give the talk. So here's the answer. The answer is we came up with this formulation which gives you a single expression that gives you the sort of an expression that has optimality conditions for it describing the best set of views, okay? And there are two terms in it. So, well, okay, there's this term here. Oh, yeah. Okay, so the R here is a covariance matrix, which tells you how the views are related. What makes it hard to pick the best views is that the views have correlated information in them, right? So you have to somehow decorrelate that information. That's why there's an inverse. Okay, then the gamma is the correlation of those views with the object itself. So that's a vector, okay? And then you get this expression, and you calculate it, and then the expression that's minimum is the best one, okay? So, and just to excuse you a little bit more intuition as to how it works. So the idea is we have this concept of the view basis functions. So for a particular object, you forward project it, and then you do filtered back projection. So that gives you essentially a one view reconstruction of the object. So each of those is a view basis function. Then this matrix is the correlation between the view basis functions, and the vector is a correlation between the view basis functions and the object itself, and then you compute this thing, gamma, R inverse gamma. It's just a simple quadratic form, okay? Now, okay, why is that a good thing? Well, it's a good thing for, I would argue, two reasons. One is that it's related to the root mean square error of the reconstruction. So it can be under certain conditions. The conditions are that you have reconstructed the object as a linear combination of the view basis functions, which is an approximation because in the end we're going to use MBIR to do the reconstruction, but it gets you, it's reasonable. And the other is that you can relate it in an information theoretic sense to the Fisher information under some kind of conditions, okay? And then what I'm going to do here is, okay, this is what I call emotional equations, okay? I don't really expect you to follow this, okay? But it's just to give you the emotional sense of what the equations are, okay? So, the idea is that you're doing a reconstruction, and the reconstruction is a linear combination of these bases, okay? And then you say, well, what's the best linear combination? Well, you go through these sets of equations. They kind of look familiar, right? And this thing here is a projection. And then you use Pythagorean theorem to reformulate the projection as the difference between the square of the two sides, you know, like, and then it comes out, okay? So that's the proof. It's really not that complicated. So then, now the problem is, how do you compute it efficiently? Well, you have to, first of all, what you have to do is you have to search over all the bases for the ones that minimize that loss function. That's just a loss function, right? So to do that, we have a randomized search strategy. It doesn't get the globally optimal solution, but it gets close, okay? And then what the other thing is that we have two other things that we have to use to make this run fast. If you do it in the completely naive way, this thing would take days to compute, okay? So you have to do it, because the object is so large, it's 1,000 by 1,000 by 1,000, so it's a gigavoxel of data, right, for each view. So first of all, you compute R and gamma only once. R is only, if you have 1,000 views that you're selecting, let's say you're selecting 200 views from 1,000, then that matrix is 1,000 by 1,000. So it's not that big, but computing each entry of that matrix could be very expensive. So the way you reduce the computation is by doing, by random subsampling of the pixels. And we integrated this all into the software package, so you don't have to worry about any of it, okay? And okay, this is what's actually in the paper. Okay, it took 7 minutes to do it for our problem. But when we, with some approximation, it's not exactly the same thing, but it's close, implemented in the software package, we used the implementation that's already in JAX, and we accelerated it by another almost factor of 10. So it takes about a minute for a large problem. So, you know, that's not an overhead that would be significant, because it takes like, you know, quite a bit of time to do the reconstruction itself. Okay, so this shows you the results, and the upshot is this, that this method consistently produces better quality than doing uniform for sure, and even heuristic methods. And in a variety of situations, and I would tell you the truth if that wasn't true, okay? But over there, so this is an 80 view case, and if you look closely, you don't get like defects along edges. It's pretty consistent. Oh, this is simulated data. Okay, now, and in this case, this is an example. If you're familiar with this problem, there's a thing called a short scan where you have to use what's called Parker weighting. So you don't really need 180 degrees. You only need, you don't need 360 degrees. You only need 180 degrees plus the fan angle. But, so we compared against that so that it would be a fair comparison. But the point is that this methodology actually self-discovers that fact, okay? And it gets like the smaller number of views, and it really does come out better. This is on real data. So over here, this is 40 views, and you can see that, hold on. Okay, you can see here that this reconstruction with 40 views using the selected view angles is much better than the uniform and better than the heuristic. And also when you make measurements of specific metrics like edge sharpness, this is what they would really care about in the application space, and the hole diameters, it's consistently better, okay? Okay, and then this is the other thing that comes up that people ask questions about. They go, well, what if your reference object is not accurate? Because, well, you can have a pretty poor quality reference object, and it still does a pretty decent job, okay? So we found it to be robust. So in summary, we sort of formulated this little piece of an important problem, which is coming up with a consistent mathematical formula for what would be a loss function for selecting views, okay? And it naturally trades off between being informative and diverse without having to have a crazy parameter that you have to pick. And it can be efficiently implemented for real-size problems. And I think in the future, there's a lot of directions you can take this in. Noise, you can incorporate noise and attenuation, arbitrary geometries, and dynamic scanning. Okay, thank you very much.
Thanks a lot, Charlie. We have time for one question.
really cool. I was just curious, because you mentioned if you don't know anything about the object, the best views are uniform. So when you do end up picking the views, do they look way different from uniformly picking, or are they just like sort of kind of uniform?
They don't look way different. And I should have pointed that out. They only look subtly different, but they produce a significantly better reconstruction. Like if you were going to, what you might think is that you would just go and draw with a pen and say, oh, I'll take a view in this direction and that direction. It's subtle, okay? It's subtle because the fan beam, not all the projections are in the same direction, okay? But also it's subtle, I mean, it's just subtle, okay? It's subtle. So, but it's consistently better. So yeah, it's capturing something in a mathematical sense.
Thank you.
Thanks a lot. The next speaker, Nalini Singh, is going to talk to us about direct atomic structure identification in electron tomography.
Thanks. Hi, everybody. I'm Nalini. I'm a postdoc in Laura Waller's group. And yeah, I'm going to tell you a little bit about our Gaussian parameterization. So the high-level goal here is that we want to characterize materials at the atomic scale. And recently, transmission electron microscopy has let us do a good job of this in 2D. So here's an example of a TEM image of a sheet of graphene. And you can see that there's a defect in the sheet that's circled in red. And we can post-process this image and figure out what the atomic structure is of this material. And then material scientists can use this to characterize the material and to simulate how it might behave under a bunch of different conditions. So we know how to do this in 2D, and the next step is we're interested in doing this in 3D. And to do this, we're going to do tomography. So we heard a lot about this in the last talk, but the idea is that we have our sample, and it's sitting on a tilt stage, and you shoot an electron beam at that sample, and you get a measurement at the detector. And so the thing that you've measured is an integral of the atomic potential in the direction of the beam that you shot. And then you repeat this process after you tilt the stage, so now you have some information about a different angle, and you keep doing this over a range of angles until you have a set of these projection measurements. And then normally what you would do is you would solve for a volume which represents the 3D structure that you're interested in. So you have some volume, you simulate the tomography forward model, and you compare that result to the projection measurements that you acquired. And then you have this loss function that you can use to optimize the values in your volume. And once you finish this optimization process, you can then run this computational post-processing step called atom tracing, which tells you what the structure of the material is. And so you can think of this structure basically as a list of the positions in 3D space of where the different atoms are. So this is fairly straightforward, but there's a couple of challenges in practice. In particular, we're interested in this missing wedge artifact. So normally you have the sample on this tilt stage, but for a bunch of reasons, there's some experimental limitations and limitations on the sample. There's a couple of ranges of the angle that you can't really access. Like you can't take measurements in these ranges. That's the so-called missing wedge. And the upshot of this is that the inverse problem that you're trying to solve is underdetermined. And because we have this sort of multi-step process, the errors in reconstruction as a result of this underdeterminedness cause problems in solving for the structure. So here's an example of a slice of a volume that you might reconstruct, and we have a zoom in of like a little patch there. And so ideally what you would want to do is take this volume and identify, you can see with the white X's, where the individual atoms are. But if you look closely, you see we have some artifacts from the missing wedge. And so if you run your computational post-processing algorithm, this will give you, for example, in this case, some atoms in places where there actually aren't any. And we want to avoid this. So for the rest of this talk, I'm going to tell you about our strategy where we're going to directly optimize the atomic structure. We're going to bypass the step of optimizing the volume. And we're going to do this in a way that helps us avoid some of these problems with the missing wedge. And so the main idea here is that we're going to use a different parameterization, which lets us incorporate some knowledge that we have about what we think atoms might look like. The idea is really, really simple. We're just going to model particles as collections of Gaussians. So many of you are familiar with Gaussian splatting. There was some reference to that earlier in the session, and we're going to draw heavily on the ideas from that here. So each atom has an atomic potential, which is modeled as a Gaussian, and there's 3 parameters that we want to optimize for each atom. we have its position. So this is where it's located in 3D space. And if you remember that the whole thing that we're interested in is a list of the positions of all of the atoms in our structure. So if we can correctly solve for this position, we've accomplished our goal and we can get the structure that we're interested in. The second parameter is the scale of the Gaussian, or how big it is. And then the third parameter is the amplitude of the Gaussian. And so in practice, this is related to the atomic number of the atom that we're interested in, and it will tell us about the atomic species that comprises our particle. Okay, so the particle is then a collection of a bunch of these atoms. So we have 3 of these parameters for all of the atoms in our sample, and we'll optimize these jointly using the same data consistency loss that we used earlier. And then an obvious question here is, how do we know how many atoms we need to optimize? And the answer is we do this dynamically over the course of the optimization. So if we have a Gaussian where the amplitude is small, we can just remove it from our structure. And if our loss gradient is high in a particular place, we'll just add gradients and then let the optimization progress and sort of solve itself. And I'll note that for our application, it's really important that we get this part right, because we need to be able to determine an exact one-to-one correspondence between the Gaussians that we learn and the atoms in the structure, so that we know that we've solved for the correct structure. Okay, so a nice thing about this parameterization is that it lets us really easily incorporate physical constraints that we know about the particle. So we'll do 2 of those. The first is that we know that atoms are isotropic, so their radius is spherically symmetric. And we can implement this by just making our covariance matrix have constant values on the diagonal. We also know that there's some minimum distances between atoms. So atoms have bond lengths and they can't be too close together. And so whenever we detect that we have multiple Gaussians that are within some threshold, we can just cluster them together into one Gaussian and then let the optimization progress. And so these are really easy and intuitive and simple with our parameterization. But I'll note that if you wanted to do this with a voxelized version, it would be much harder to express these ideas. Okay, so we'll test our method on this data set of 4 particles, first in simulation. And we've chosen these particles to vary in the number and type of atomic species, the number of atoms in the particle, and how periodic each sample is. And we simulate our data as follows. We start with the structure, and then we simulate projection measurements according to the forward model. And we have sort of 2 modes that we do this in. The first is a full data mode, where we simulate every angle from minus 90 degrees to 90 degrees, and then a limited angle mode where we simulate every 3 degrees from minus 70 degrees to 70 degrees. And that's to simulate the missing wedge artifact I was talking about earlier. We then apply a blur kernel corresponding to the PSF of the microscope, and then we add some noise to the sample. And we compare to a couple of baselines. So we have 2 classical algorithms and then a self-supervised deep learning approach. And for all of the baselines, we first do a volumetric reconstruction, where you get a slice that looks like this. And then we run the atom tracing step, where we go from the volumetric reconstruction to the locations of the atoms in the sample. And so in practice, we implement this with a peak finding algorithm that incorporates some minimum distance constraints. Okay, so here's a sample result on the full data case for all of the different methods. And you can see that all of the reconstructions do pretty well. So if you look at the zoom-ins, you can sort of see where each atom is in the sample. And then we run the atom tracing step, and computationally that's also the case. So here's the visualization where we have black dots representing correctly found atoms, red representing false positives, and green representing false negatives. And on the slide you can see it's almost entirely correctly found atoms, so all of the methods are doing well. The story is a little bit different when we go to the missing wedge case. So you can see that filtered back projection, SART, and the INR have some streaking and other artifacts in the reconstructions. And our method doesn't. And so the reason for this is that our parameterization basically doesn't let those artifacts exist in the way that it's parameterized. And this translates into better atomic structure identification. So if we look at the same visualization as from before, you can see right off the bat that filtered back projection produces a bunch of false positives. And then if we look at some of the locations for SART and the INR, you also see some errors there, whereas our method gives almost entirely the correct structure representation. So this is just an example of one particle, but this result holds across all the particles in our data set. So each of these plots show on the x-axis the different particles in the data set, and on the y-axis here is SSIM, so a reconstruction quality metric, and you want to be higher on this plot. And so in the full data case, our method is comparable to the best next method, and in the limited angle case, we outperform all the baselines. And then similar quantitative results hold for the true and false positive rates for identifying the atoms. So in almost all cases, all the methods do well in terms of the true positive rate of identifying the different atoms, but other methods tend to identify many more false positives in the limited data case than ours does. Okay, we can also look at the result of the physical priors that we imposed on our representation and show that it really helps us get good atomic structures. So here's a visualization of one slice of a carbon nanotube, and it's the same structure of the visualization that we were looking at before. But we're looking at now an ablation study where the first column shows the results from our method, and then the next columns show what happened when you remove either the isotropy or the minimum distance constraints that I described earlier. And so you can see that if you don't have any of those constraints, you typically end up with more Gaussians than atoms than in the sample. And so in practice, this is because if you have a bunch of really small Gaussians in the same place as a big Gaussian, this will give you similar simulated projection measurements. But it'll give you the wrong atomic structure because you have more atoms than are actually in your sample. These physical constraints also help us do atomic species identification. So if you recall, I mentioned that if we correctly solve for the amplitudes of the Gaussians, this will tell us something about the atomic number of the things in our sample. And so these are histograms for each of these cases, where the x-axis shows the amplitudes of the different Gaussians, and the y-axis shows how many of those we have in our particular particle. And so the ideal setting here is that we want the Gaussians corresponding to different atoms, atomic species, to be separated on this histogram. And so you can see that that's the case in the first setup, where we have all of our physical constraints, but you lose that if you remove the physical constraints. The last result I'll show is a proof of concept result on real experimental data from the microscope. And so here we were imaging a carbon nanotube with some known structure, which is shown on the slide. And then here are the reconstructions from a bunch of different methods. So this was a previously, solving for the structure was a previous work, which the result of that was shown in the first column. The second column shows the result of our deep learning baseline, and then the third column shows our Gaussian splatting approach. And so none of these reconstructions are perfect. Like you can see, there's artifacts in all of them, but the atoms are much better defined in our reconstruction than in the two baselines. Okay, so we're really excited about this, and we think it could be really useful for modeling more complex dynamics than what we've already done. So here's an example of some real data that's a bit more challenging to reconstruct than what we've done already. This is a carbon nanotube, and you can see that there's this stuff growing on the outside of the nanotube. And so this is something that happens over the course of acquisition. Basically, between one projection measurement to the next, you have this stuff growing on the nanotube. And it's pretty hard to model that, write down information about that process if you have a voxelized representation, but it's a bit more, we think it may be a bit more intuitive to do that with a representation like ours, or more generally, to represent dynamics of the sample over the course of the imaging process. Okay, so to summarize, we've shown that our Gaussian representation really simplifies the atomic structure identification process, and it improves the robustness to various artifacts that arise in atomic electron tomography. And we've shown this both in simulation and in a proof of concept experimental result. So I'd like to thank my collaborators and also our funding sources, and really happy to take any questions.
Thanks a lot. We have time for a couple of questions. Yes, back there. Okay. You can
go first?
Yeah.
Thank you for the presentation. So I saw that you can dynamically change the number of Gaussians and by either removing some Gaussians or increasing the number of Gaussians. Did you do this by some predefined threshold on the strategies?
Yeah, so this is actually this dynamic optimization strategy is part of the regular Gaussian splatting setup. That's not a new thing about our method. And they do have predefined thresholds, which you have to set, you have to figure out what they are. For our data set, we use the same thresholds for all the samples. So it seems like for a particular imaging system, you can be somewhat robust to variations in the sample for that.
Okay, thank you so much.
Yeah.
Yeah, so I had a question about the physical interpretation of the quantities that you recover. So for example, you have to impose these minimum distance threshold distances. Does that mean you're recovering the size of the Gaussians in metric units? And also for the amplitude of the Gaussians, I noticed that they're the scales seemed arbitrary in the horizontal axes. Is there any significant correlation between the amplitude and the actual atomic weight of the atoms, or does just the relative amplitudes give you a sense of the relative proportions of the different atoms in the particles?
Yeah, I'll answer them in opposite order. So for the amplitudes, it's definitely just the relative. We know the ratio of the atomic number is roughly the same as the ratio of the quantities recover, but the quantity recover is not exactly the atomic number.
Yeah.
And sorry, I forgot your first. The minimum distance constraint, does that correspond to physical quantities? Was that your question?
Yeah. So it's actually like, I don't know, like nanometers or something, or whatever the scale is.
The answer is no. So in practice, we do the optimization not in physical, like we scale physical space down to some arbitrary units for ease of some hyperparameter settings. But also, so in practice, the threshold that we set for the minimum distance isn't exactly the bond length, because we tried doing stuff like that, but during the optimization, you need atoms to be able to pass closer together than the bond length to like progress to the correct location. You could try something like relaxing the threshold as the optimization progresses, but we have not done that yet.
Okay, thank you.
Thanks a lot. Let's thank the speaker again. And of course, speakers will be available for more question and probing during lunchtime. So our last speaker, Pablo Luesia, is going to talk to us about zero-phase phasor fields. And take it away.
So thank you very much. Oh, wait. Thank you very much for the presentation, but our paper is we decided to update during the reviewing process. So this is a collaboration between our University of Zaragoza and the University of Wisconsin-Madison, sorry. Let me start showing the no line of sight setup. This is a common setup where we target to reconstruct this dragon that is occluded behind a corner. And we want to achieve this image and identify what is this geometry. This has many applications, for example, car safety, where we will warn the driver about danger that is outside their line of sight. Rescue operations, where the rescuers could identify the people they want to actually save without risking their lives. Or medical imaging, well, we could develop less intrusive methods for diagnosis for medical illness. So, current problem is that, okay, actually there are some non-line of sight methods and now they are achieving some promising reconstructions and they are doing it efficiently, but they struggle right now to identify the depth correctly when it comes to very small variations. This could be the correct depth, but it took a long time to estimate. On the other hand, if we use the usual implementations, this will take efficient time with some error. Here we propose our zero-phase phasor fields that employs the phase to add small overheads compared with these efficient implementations, but can achieve much better depth resolution. Let's start with the no line of sight imaging setup. We have here our hidden scene that is also our line of sight because we have an occluder in the middle, and we have the relay wall that we're going to employ to identify this hidden scene. So first, we emit our ultra-short pulse of light into a point into the relay wall, and the relay wall will scatter this short pulse of light into the hidden scene. The hidden scene, at the same time, will take this illumination and it will scatter it back into the relay wall, when we can capture with our camera. But this camera is not a common camera, it's an ultra-fast camera, and it can capture transient imaging, which means that at very high frame rate resolution, we can capture the light in motion. Then we focus our camera into the same point we use for illumination, which gives us confocal capture. And then we capture the indirect illumination from the bunny to obtain something like this, where we can observe the arrival of the photons decoupled by time. Instead of a single point, we're going to use a grid of points, and then we capture something like this, when we can identify the indirect illumination from the bunny reaching the relay wall. So the problem is, how do we employ this information? Well, as I've mentioned before, there is a bunch of non-line of sight methods. We have filtered back projection, light cone transform, FK migration, Fermat paths, and the phase-of-phase formulation, to name a few. But, as I mentioned before, these methods struggle to find small depth variations within a saying of the range of the meter scale. Now we're going to focus on the phase-of-phase formulation. we have here our lateral view of our setup. We have the relay wall on the left, and then we have our hidden scene on the right. Remember, we also have an illumination and capture point. The phasor fields can use the capture of one of these illumination and then can modulate it with a virtual Gaussian wave packet, with a convolution by time, results into a virtual phasor. Applying this to all the captures we have from a relay wall, instead of having captured photons by signal through time, we're going to have our phasor fields, which gives the name to the formulation. So the problem now consists on defining an imaging point, and then we propagate our phasor field into this point. This results into a phasor as image point, which contains two values, the amplitude and also the phase. There is also efficient implementations of phasor fields that can propagate instead from the plane to a point, from the plane to another plane. So how does phasor fields identify the geometry of this hidden scene? Well, we can define the image points in a line, and we assume this is continuous. So we have in the amplitude something like this, where the exact position of where we have the hidden scene, we're going to have a maximum in the amplitude. Phasor fields employ this efficient implementation of propagating plane to plane to voxelize this volume into different planes. And then, just looking at the amplitude, we can select the maximum, which gives us this plane. That, in this case, is the closest plane to the surface. However, there is a big problem here. As you see here, there is a small gap between the actual reconstructed plane and the hidden surface. We could diminish this gap, increasing the resolution by increasing the amount of planes, but therefore we will increase the execution time. There is where our zero-phase phasor fields come. If you remember, our reconstruction not only have the amplitude, but also we have the phase. So our method employed the phase that was previously discarded by previous methods. If we now focus on the phase, and specifically on this part over here, let me zoom in, we can see that we have the image plane in orange, or bunny position, that is this hidden scene in this case, in purple, and then we have in green the phase evolution through the hidden scene. But if we look closely over here, we have the key observation of this paper. The image phase crosses to zero at the true surface positions. Then we can leverage that we know the phase at the image plane to employ the phase and correct this mismatch, and then estimate the correct depth correctly. Summarizing, we have three methods. We have the phasor fields, that image planes, and then selects the maximum in the amplitude. We could also implement a dense phasor fields that basically is same as phasor fields, but incrementing enormously the amount of planes to have better depth precision. And then we have our zero-phase phasor fields that applies a phase correction, and then we can image the planes, then select the maximum in the amplitude, and then correct the depth using this phase information. Now we sift through the results. In this case, we have the simulation of a plane that is located at 1 meter from the relay wall. Here, we're showing the top view as such simulated plane, and we can see the ground truth in purple. The phasor fields, when estimating the depth, it has a small offset because, in this case, it's an offset around 5 millimeters, because we're not accounting exactly for the hidden surface position, but to the position of the image plane. If we apply our zero-phase phasor fields, we diminish this gap, we make it closer, and we can observe that instead of 5 millimeters, we're reaching roughly 1 millimeter gap between the ground truth. However, if we manage to split the plane and move it 500 micrometers into the depth, we get something like this. We can observe that there is a small step in the depth. Again, phasor fields cannot account for this depth because it's reconstructing again the same image plane. But our method not only diminishes this gap, but we also account for this step over here associated to the variation. So we can say that our method recovers micrometers depth variations. This is even possible to observe even in an extreme case of 125 micrometers instead of 500. And let me put a line here for reference. We can still observe here that is a small gap we can still report. Now we shift to real capture. In this case, we're using a publicly available dataset. And we employ the dense phasor fields to estimate the correct depth that we are going to use as a baseline. For reference, this took almost 9.5 hours to estimate this correct depth. And here we are showing the phasor fields comparison, the difference with this baseline. In this case, we're achieving a much better time efficiency, But if we compare with our method, we observe that we report less error, our difference is less, and we're also having same time or same efficiency as before with a small overhead associated to this phase correction. Finally, we're showing the results of decreasing signal-to-noise ratio. And it's common to non-line of sight to have almost to have long exposure time, to have the capture less noisy as possible. But in this case, we're going to be using less exposure time to decrease the signal-to-noise ratio. As we can see, the phasor phase amplitude, in this case, retrieve the geometry guide. We can see the amplitude, and we can identify the dragon very precisely. And if we look at the depth of our estimation, we can see these small depth variations with smooth variations, and we can observe this depth small details. If we decrease the exposure time, we can see in the amplitude that we're getting we're getting more noise in the amplitude, but we're still capable to obtain this depth. But if we go to even less exposure time, we struggle to see the edges of the dragon in the amplitude, but we still manage to obtain this smooth depth variation associated to the position of the hidden scene. We can even go further and use this 15-second exposure time when we no longer can identify the dragon. But when we look at the depth, we see that ours is capable to get these depth variations with some errors in the edges of the dragon. So in conclusion, we have three methods where we've been speaking about three methods. We have phasor fields, which is efficient in time and in memory, but it doesn't have that much depth precision. We could increment the depth precision by incrementing the amount of planes, giving us the dense phasor fields, but this gets inefficient in time and memory. And we propose our zero-phase phasor fields that, using the same efficiency as phasor fields, we manage to get higher depth precision. So in conclusion, we've devised a method that accurately estimates micrometer scale depth variations, and also we've shown that recovering this depth is robust to the noise by using the phase. As future work, we account for near-field diffraction that we think it might be causing the small mismatches we have observed in previous results. We want to thank to the Graphics and Imaging Lab and the Computational Optics Group for their assistance, and also to all the funding of this project. Thank you very much.
Thanks a lot. Any questions for our speaker? Was there a question? Oh, way back there. Yes. The microphone is coming to you.
Could you give us some insight on, maybe you mentioned it and I missed it, why does the zero phase correspond to the true object depth? So, to put another way, right, waves, right, the phase, any global shift of the phase should not change the wave itself. So there should be nothing special about a zero crossing. I can just add a global constant to the phase, and the phasor should remain, the phasor field should remain the same. So what's so special about the zero crossing? Why does it work? And sort of an add-on to that is, why is there a bias in the results that you showed? You're clearly able to get the edge, but it seems to be biased. Could you, any insights on why that bias happens?
Mm-hmm. So for the first question, we're not using exactly like the real phase. Let me look for the slide. Instead of using the
see your slides.
Oh. Is it?
Sharing your screen. Screen share.
Oh yeah. Okay, thanks. So the face we're talking is not the real face. This is a virtual one, because when we're capturing our signal, we are modulating with a virtual signal that in this case is this virtual Gaussian wave package. We can modulate the virtual Gaussian wave package as we wish. So we can modulate its phase whatever we want. And then it comes the second part that I didn't enter in much detail because of the lack of time. But then when we propagate into these imaging positions, the results act as it's acting like an emitter in the reconstructed scene. So we're having this point over here, if the hidden position is exactly there, it's acting as this virtual Gaussian wave package illuminator. So controlling the illumination allows us to control the zero phase. So the zero phase is something that we make it to happen, but we have to control the illumination. And about the second question, I think you were talking about the small bias that happens into the results. Let me look for them. So sorry. So the mismatch, we guess that the mismatch is happening because there is some near field diffractions. We're not accounting for them because we can see the bias you mentioned before in the depth, even if we're not using just the phase correction, but also the dense approximation of using this reconstruction. So our guess is that we, in our work, if you look at the paper, we assume that this is happening from a delta point in space. But there must be there are some near field interreflection between the different points that we think affect the overall phase estimation.
Okay, thanks a lot. Let's thank all of the speakers again.
Aviad, I think there's one more.
We can take more questions. Pablo is going to be here, and so people can take the questions in lunchtime. Thanks a lot, Pablo. So before you guys go, we have poster demos.
All right, thanks. So before we break for lunch, we'll be coming back 2 to 3:30 p.m. right through these doors. We're going to have posters and demos. We'll have some tomorrow as well, but they're different posters, different demos. You're definitely going to want to come to both. Today, we're excited to feature the Best Paper Honorable Mention, as well as these highlighted works.
Sequence of short laser pulses and detects individual photons with a single photon detector, such as a SPAD. Typically, the times between a laser pulse and a photon detection are collected into a histogram, which can be used to estimate a distance as well as the signal flux, which is proportional to reflectivity. In this work, we introduce Doppler single-photon LiDAR, which enables simultaneous estimation of distance and velocity for moving objects. Velocity estimation is made possible by measuring the Doppler shift between the transmitted pulse train and the received detection times. The laser transmits a periodic sequence of pulses. The pulse spacing in the received light differs from the transmitted pulse period if the illuminated spot is moving toward or away from the LiDAR. Here we show a sequence of experiments validating our method. First, we investigate linear motion. When the signal-to-background ratio, or SBR, is high, we can estimate distances with sub-centimeter accuracy and velocity estimates with root mean squared error around 5 centimeters per second. Even when the ambient light is much stronger and the SBR is much lower, we can still recover good distance and velocity estimates. Finally, we can reconstruct an entire 3D video that shows signal flux, distance, and velocity all in one. Because we use a single element detector, we raster scan the scene to capture point-wise estimates over time. These estimates are then time synchronized using an angular encoder connected to the fan motor. This demonstrates the information that could be captured with an array detector and flash illumination. In summary, our Doppler single-photon LiDAR approach is able to simultaneously measure distance and velocity, as well as background and signal flux.
In this work, we present event fields, which use event cameras to capture light fields at high speed, resolution, and dynamic range. RGB cameras struggle to capture high-speed, high spatial resolution videos as they require massive bandwidth. Event cameras reduce bandwidth requirements by capturing sparse brightness changes for all pixels asynchronously. Light fields are another technology widely used in imaging and vision for advanced scene understanding, enabling features like refocusing and true depth estimation. In this work, we combine the best of both concepts and develop event fields. Using innovative optical designs for event cameras, we can now capture light fields at high speed, spatial angular resolution, and dynamic range. Event cameras only capture spatial and temporal information, while event fields require angular information. Therefore, we multiplex angular information into either the spatial or temporal dimension, with each having their own relative merits. For spatial multiplexing, we use a rectangular kaleidoscope design inspired by Manakov's work, which allows us to capture a 3x3 grid of angular views, with each view at 1/3 spatial resolution. For temporal multiplexing, we place a galvanometer in the optical path of the event camera. By moving the mirrors of the galvanometer at high speeds, we capture angular derivatives of the scene at full spatial resolution. We developed hardware prototypes for both designs to test on real-world scenarios. Thanks to the event field's high dynamic range, we can now capture snapshot HDR light fields. The scene here has both bright lights and a dim texture. Event fields can capture both at the same time. With the galvanometer setup, we capture a full-frame light field at 40 angular views and 250 FPS. This allows us to post-capture refocus a fan rotating at 300 RPM. We combine the event field data with RGB frames to capture a color event field. We then use the time lens algorithm for slow-motion refocusing. Here, we show the ability to focus on a fast-moving Nerf dart. Our technique can focus on the fly. We also demonstrate true depth estimation, a common light field application now enhanced with slow-mo capabilities. We believe our work on event fields will inspire others to explore new imaging and vision applications with high speed, high resolution, and high dynamic light fields. Thank you for listening.
Rapid wavefront shaping using an optical gradient acquisition. When we image in thin tissue, we're able to get nice clear images. However, when we try to image deeper inside the tissue, scattering from earlier layer causes aberration on the image. In wavefront shaping, we introduce a spatial light modulator to undo the scattering to achieve a sharp image of the object. In this work, we introduced the fast wavefront shaping algorithm. To find the optimal modulation, we describe our problem as an optimization problem. We define a confocal scan function where the score measures the intensity reaching the central pixel of the sensor. In this work, we use the sum of confocal intensity over a small window inside the tissue. Previous approaches relied on slow algorithms which query each parameter of the modulation sequentially. However, these algorithms are slow, and this is especially true for thicker tissues where the correction requires many parameters to undo the scattering. In our work, we explicitly write the analytical gradient of the score, and although the gradient depends on the reflection matrix of the tissue, which is unknown, we show we can rewrite the function so it depends on the reflected light and not on the unknown tissue structure. Hence, by capturing the reflected light, we can calculate the gradient of the function and perform gradient descent, which optimizes all SLM pixels simultaneously. Here, you can see an example where we start with a uniform SLM phase, and then each iteration capture the gradient and update the SLM phase accordingly, resulting in a sharp spot after a few iterations. This is a few orders of magnitude faster than previous approaches. We present several results of our algorithm imaging a chrome mask, sparse polystyrene beads in agarose gel, and the boundary between two onion cells.
Hi everyone, I'm Mohammed, and today I'm going to present Pandora, Casual HDR Radiance Acquisition for Indoors Needs. This work is a collaboration between University Laval, Adobe, and Texas A&M University. Capturing high dynamic range radiance is essential for virtual object insertion, which is the foundation of visual effects, augmented reality, and virtual photography. The related work in this field addressed this problem by using expensive equipment. In this work, we present Pandora, panoramic dual observer radiance acquisition. which is a novel system for casual HDR radiance acquisition without any expensive equipment. The main focus of our system is to capture the lighting intensities. Pandora uses two 360-degree cameras attached to each other. One camera is set to capture the general appearance of the scene, and the other camera is set to capture the intensities of the light sources. We capture HDR radiance by casually walking through a scene. Here is how our two captured sequences look. We have two main challenges in this pipeline. The first challenge is that the fast exposed sequence is too dark for structure from motion. We propose a self-calibrating method to address this issue. The other challenge is that the two capture sequences are not aligned. We propose a two-stage training approach for nerves. For more information, please check out our poster number 8 on Monday. Here is the result of our LDR nerve baseline. The virtual object looks dull and unrealistic. Here is the result of an HDR nerve method. This method produces a lot of artifacts. In comparison, our method produces realistic virtual object insertion with way fewer artifacts. Thanks a lot for your attention, and for more information, please visit our website.
In this manuscript, we introduce a Monte Carlo rendering framework for simulating optical heterodyne detection, bridging the gap between traditional rendering algorithms and optical system simulation. Heterodyning is widely used technique in electrical engineering that mixes input signal with reference signal, creating a signal at difference frequency, also called beat frequency. Optical heterodyne detection, or just OHD in principle, is same with electrical heterodyning, but now heterodyning is performed by optical interferometer with using of coherent light source. The beat frequency now arises as AC term and photon induces current measurement and interpreting the power spectrum. We can know useful information encoded in the optical signal, such as Doppler shift or distance to the object. In this paper, we propose a scalable Monte Carlo simulator that can reproduce this OHD power spectrum under various configurations. Using our simulator, which leverages rich modeling and sampling capabilities of existing Monte Carlo path tracers, one can simulate diverse OHD applications, such as FMCW LiDAR in autonomous vehicle, non-invasive blood flow measurement, or atmospheric Doppler sensing. Thank you for listening.
We present NEST, a polarization-aware inverse rendering approach to turn cameras into force sensors. Mundane everyday objects show these beautiful fringe patterns when placed on a polarized screen and viewed through polarized glasses, because the mechanical stress field hidden inside these objects alters the polarization of light. Now, for a thin planar object, there is a one-to-one correspondence between the density of fringes and the amount of stress. But this correspondence breaks down in thick 3D objects loaded with forces in arbitrary directions. Traditional approaches required manually slicing the object and using this correspondence to deal with each slice. However, this approach is slow, expensive, and most importantly, destructive. We present the first method to recover stress tensor fields hidden inside 3D objects in a non-destructive manner, without any manual slicing. Our approach involves first capturing fringe patterns from many angles with a new multi-axis polariscope setup, and then solving an inverse problem to recover stress tensor fields from these fringe patterns using a differentiable rendering and neural implicit representation approach. To demonstrate NEST, we first apply compression forces using clamps on translucent 3D objects, then we capture that multi-axis fringe patterns, and then recover the internal stress tensor fields, recovering components of each unknown force. From the estimated stress tensor field, we can also virtually slice the object. We show that the estimated fringe patterns of each slice match what we would actually get by slicing the object. So with applications in microscopy, robotic manipulation, and infrastructure monitoring, NEST points towards a new paradigm of turning cameras into force sensors.
I'm excited to introduce HiSPED, our system for video rate hyperspectral inference using single-photon sensors. HiSPED is a scanning-based video rate hyperspectral imager. Our lab prototype achieves 123 spectral channels at 26 fps without any compressive sensing. Capturing hyperspectral video is challenging due to extreme light sparsity across space, time, and spectrum axes. Under this low light scenario, conventional CMOS sensors suffer from significant readout noise. As a result, CMOS-based hyperspectral video often becomes unusably noisy due to its low light conditions. To overcome this readout noise, we leverage Sparse sensors, single-photon detectors that are inherently readout noise-free. Our system uses a Sparse sensor in a scanning configuration to achieve high-resolution hyperspectral imaging. We call this method HiSPED, hyperspectral imaging with Sparse sensors. However, SPED-based spectral measurements are still noisy, highly quantized, and nonlinear. Therefore, we provide theoretical guarantees for spectrum reconstruction and material classification with experimental validation and multiple full spectrum reconstruction methods. Here, we present results captured using our HiSPED prototype operating at video rate. The raw hyperspectral video contains 123 spectral channels from 445 to 908 nanometer wavelengths. For comparison, we simulated CMOS-based capture with realistic readout noise. And below is the HiSPED measurements under identical conditions. Now let's look at outdoor scenes captured in sunny conditions. We also show results from cloudy day captures to demonstrate robustness. With HiSPED, we demonstrate 3 applications enabled by real-time hyperspectral video. First, we simulate scene relighting by dividing out the known light spectrum and multiplying in new illumination. Second, we render videos as they would appear through different camera spectrum sensitivities. Third, we perform per pixel material classification at video rate using a cosine similarity classifier and spectral dictionary. Thank you. Please visit our poster and read the paper for full details.
Traditionally, surgeons have relied on stereo microscopes for depth perception. These systems split light from the surgical area into 2 separate views, one for each eye, creating a 3D effect. Modern operating microscopes use digital sensors to capture these views, allowing surgeons to see the surgical field on a digital 3D display. While stereoscopes give surgeons a strong sense of qualitative depth perception, it's very challenging to actually measure precise distances and shapes or quantitative depth information from the just 2 unique camera views these scopes provide. Our solution to this challenge is the Fourier Light Field Array Microscope. Instead of relying on just 2 camera views, this system packs 48 microcameras into a compact space. In a single snapshot, this system captures high-resolution images of the surgical area from 48 unique perspectives simultaneously. As the surgeon works, the FLFA can stream images at up to 120 frames per second. We can take a single snapshot from the system and feed it through a custom 3D reconstruction algorithm to produce a detailed depth map, which can be displayed to the surgeon as an interactive 3D model. Our tests have shown that the FLFA successfully reconstructs depth maps across a 1 centimeter range with precision down to 10 microns. In our demo, we will show how by combining our compact camera array with a variety of high-throughput optical components, we can generate 3D visualizations for a wide range of applications.
All right, come back for these and more at 2 p.m. through those doors.